Okay, so in this example problem, we're going to be going over an application of Bernoulli's equation where we use it to determine the pressure required to get a flow rate through a certain nozzle. And in this case, we're going to ensure that we adhere to all of the very specific assumptions that Bernoulli's equation requires for its use. So to start, we're going to look at our nozzle here. And our nozzle starts off with this diameter D1, a larger diameter D1, and converges into a smaller diameter D2, where after D2, we have free atmosphere as indicated by this P infinity. The control volume of our nozzle is indicated by this orange dotted line, and we're going to be looking at a streamline, or a parcel of fluid, that goes from point 1 to point 2 in a straight shot, just like that, right? So let's go over our assumptions, and these assumptions are very specific to Bernoulli's equation. So 1, we're going to assume that we have a steady flow, so none of our field variables change with time. 2, we're going to assume we have a constant density flow, so constant temperature, incompressible, etc. 3, we're going to assume that we have a frictionless flow. That's very important for Bernoulli's equation. We're going to assume we have a frictionless flow. Many flows you cannot assume are frictionless, but for this case, we're going to assume the flow is frictionless. 4, we're going to assume that we have negligible turbulent kinetic energy. So this streamline that we're looking at from 1 to 2 is a straight mean streamline. There's no noise signal that is superimposed on top of it by turbulence or anything like that. So we could just look at this kind of idealized linear streamline. 5, gravity is the only body force, so we don't have to worry about magnetic fields, electric fields, anything like that. And 6, our velocity and pressure are uniform at sections 1 and sections 2. Right, so this section right here, velocity and pressure are uniform. This section right here, velocity and pressure are uniform, or reasonably approximated as such. And with that, we want to derive an equation for the minimal gauge pressure required to produce a given flow Q. What we need to realize here is, as we introduce friction to this system, as we introduce friction to this nozzle, that friction will increase the required pressure to get a given flow rate Q. So as we introduce friction from the shear stress on the walls, as we introduce friction from the separation in the corners, all of that entropic loss, all of that friction will increase the required pressure to get a certain flow rate Q. So when we assume a frictionless flow, that's going to give us the minimal physical pressure that could produce that flow rate in a completely ideal scenario. In reality, the required pressure because of friction will be much higher than this, right? But this can kind of give you a thermodynamic limit of what the minimal pressure is to produce this flow in a completely ideal system. And we're going to be looking at that ideal case here. So now the equations we need to solve this problem are Reynolds transport theorem and Bernoulli's equation. Reynolds transport theorem, I'm going to assume that you have a familiarity with it, but just to kind of broadly overview it, it's essentially saying that the time rate of change of some field variable n within a fluidic system is equal to the time rate of change of that variable within a control volume plus the net outflux of that variable from the control surface. And we'll go over the application of that on the next slide. Bernoulli's equation is from a previous video where we derived it, and it essentially says that the total pressure of the flow is equal to a constant. So P1 over rho plus V1 squared over 2 plus GZ1 is equal to P2 over rho plus V2 squared over 2 plus GZ2. So now we're going to look at conservation of mass through the lens of Reynolds transport theorem. And to start, we're going to remind ourselves what the system is in Reynolds transport theorem. The system in Reynolds transport theorem refers to the matter passing through the control volume at the time of analysis. So in this case, the system is the mass of fluid within this control volume at the time we're analyzing the problem. Now, the time rate of change of that mass is 0 because it is a fixed amount of matter, and we know that matter is neither created nor destroyed through conservation of mass. So when we pick our field variable of interest n for Reynolds transport theorem, which is in this case mass, we see that dm dt of the system, or the time rate of change of mass of the system, must be equal to 0 through conservation of mass. And because we have a steady system, we know that the time rate of change of mass within the control volume also has to be equal to 0. So this also goes to 0. So we're just left with this flux term. This flux term basically says that the net outflux of mass through the control surface has to be equal to 0 in this case. So we have here, through conservation of mass, that the integral of the control surface of rho v dot dA is equal to the integral of the control surface 1 of rho v dot dA plus the integral of the control surface 2 of rho v dot dA is equal to 0. And what this is saying is the mass flux coming in through control surface 1 has to be equal to the mass flux through control surface 2 in magnitude, right? So the net outflux of mass through this control surface has to be equal to 0. We have no mass flux on this top surface. We have no mass flux on this bottom surface. So we only have a term in the flux integral for control surface 1 and control surface 2. And to remind you, eta is the variable n per unit mass, and if n is equal to mass, then mass per unit mass is equal to 1, so eta is equal to 1, and that's how we get this rho v dot dA as the integrand in these integrals. So because we've assumed a constant pressure and velocity at control surface 1 and control surface 2, or in other words, a uniformly distributed pressure and velocity at control surface 1 and control surface 2, we could break down these integrals into algebraic expressions. And the algebraic expressions are as follows right here. So this equation in an algebraic expression is simply negative rho v1a1 plus rho v2a2 is equal to 0, where this algebraic expression corresponds to this integral, and this algebraic expression corresponds to this integral. And again, that's only possible because we assumed that the pressure and velocity are essentially constants at control surface 1 and control surface 2. If they were distributions, we would actually have to perform the integrals. But in this case, we can simply use this algebraic expression. So because the density is constant, it drops out of this expression right here. And effectively, this equation gives us V1A1 is equal to V2A2. Or in other words, Q1 equals Q2 equals Q, where Q is the volumetric flow rate equal to V times A. So that is our conservation of mass result, that V1A1 is equal to V2A2. Or in other words, the volumetric flow rate through control surface 1 is equal to the volumetric flow rate through control surface 2. So for Bernoulli's equation, we're going to start with the base expression as shown here, where the total pressure is constant. Because we're assuming that we're looking at a mean streamline going straight to the middle of the cone with a negligible amount of turbulent kinetic energy, in other words, with a negligible amount of noise in that streamline, we can assume that point 1 and point 2 are of the same elevation, right? Because if we had a bunch of turbulent kinetic energy, we had a bunch of turbulence effects, then our elevation at point 1 might not be equal to our elevation at point 2, but because we're ignoring turbulent kinetic energy, we're ignoring turbulent viscosity effects, we could just kind of idealize our streamline as a straight shot through the middle of the cone, and so our Z1 is equal to our Z2. So in this case, we have P1 over rho plus Q1 squared over 2A1 squared equals P2 over rho plus Q2 squared over 2A2 squared. How did we get that? Well, we know that Q is equal to VA, so we're just replacing V is equal to Q over A, and that's how we're getting these expressions right here in terms of Q. So now for our first set of simplifications, you have that P2 is equal to P infinity. And the reason we could say that is because we have a free stream jet. When you have a jet in an ambient atmosphere, or you have a jet in an ambient chamber, you could effectively say that the pressure within that jet is equal to the ambient pressure. It's a common assumption. It's called the free stream jet assumption. So P2 could be taken as P infinity, right? So that's where this substitution comes in, where we replace P2 with P infinity. The next substitution comes from conservation of mass, which we solved on the previous slide, where Q1 equals Q2 equals Q. So because Q1 equals Q2 equals Q from conservation of mass, we can take this Q1, we can take this Q2, and just replace it with Q, where Q is just the volumetric flow rate through the nozzle, through the cone. So now we have this expression right here. And what we can do is solve for P1 minus P infinity over rho. What is P1 minus P infinity? P1 minus P infinity is the gauge pressure at point 1. It is the pressure relative to atmosphere or relative to ambient at point 1. That's exactly what we're looking for. So P1 minus P infinity is P1G, or the gauge pressure at point 1. Now all we have to do is simplify and solve for P1G. When we simplify and solve for P1G, which just involves this algebra right here, I'll let you look at this at your own pace, but when you solve for P1G with this expression right here, what you end up getting is P1G is equal to the quantity 8 rho Q squared over the quantity pi squared D1 to the 4th times the quantity D1 over D2 to the 4th minus 1. And this is a very interesting result because it effectively says that if you want to double your flow rate, you need to quadruple your pressure, right? It's a quadratic relationship. And this is for the frictionless case. If you start adding friction to this system, so again, you add viscous shear in the walls, you add separation in the corners, etc., this relationship becomes even less generous than this is. This is the ideal case. In the ideal case, to double your flow rate, you need to quadruple your pressure. This is kind of your baseline. This is the minimal pressure required to get this flow rate through this nozzle. It'll never be this low because you'll never have a frictionless system, but it gives you a thermodynamic limit for how this type of nozzle or cone can perform. So again, this expression allows you to establish a theoretical limit on the pressure that would be required to produce a flow rate Q through a nozzle or cone. It will always be higher than this pressure to produce any given flow because of friction, but it can act as a useful design tool to determine, am I even within the realm of physics with this nozzle that I've designed to produce the flow rate I need with the pressure I have available to me? If the answer is no, you know that there's really no optimization of friction you can perform to get that flow rate Q for your given pressure. You just need to change the nozzle. Exercises like this can give you a very quick and useful way of determining if you're even in the right ballpark for what you're designing. Okay, so that should be it for this video. I really appreciate you watching. Thank you very, very much, and I will see you next time.